Hello, welcome back. Today, we're going to cover Kotlin generics, type erasure, and reflection. In Kotlin, classes can have type parameters, similar to how they do in Java. Let's look at an example. Let us assume we have a class known as animal. This class could probably have a specific type of animal, either a bird, an amphibian, whichever. For us to add this type, we are going to use a generic. Types in Kotlin classes and interfaces can be provided using the angle brackets. These types can be specified using any character of your choice. Most of the time, we use T as the default one. We could also have the constructor of this class to accept a parameter of that type. To create an instance of such a class, we simply have to provide the type arguments. Let's create two sample types of animals. To create an instance of such a class, simply provide the type arguments. Sometimes the parameters can be inferred. For example, if we provide an object of type fish inside the animal parenthesis, then the type parameter in the angle brackets are now unnecessary. Another example would be maybe if we had an animal that is represented as a digit. That would also work. As long as the type is known by the Kotlin compiler, it will infer it. Sometimes, with generics, you may want to have your type parameter to be used in a specific context only. This is known as variance. There are several ways in which you can provide variance within your generic types, and this is by two main approaches in Kotlin: declaration site variance and use site variance. A type that can be used to provide input and also get output as that specific type is known as an invariant type. A type that can only be produced is known as a covariant type. And a type that can only be used as an input is known as contravariant type. Let us start with a covariant type. To declare covariant types, we usually use the modifier out inside the type definition in our angle brackets. Let us have an example. In our current class definition, known as greeting, it uses the out modifier within the type parameter t. This means that whichever type that will be provided for this greeting class, it can only be used as a return type and it can never be used as an input in parameters. You could have a function that provides that output. This is acceptable syntax, whereby you'd have a function known as hello, which returns the type t. Within this, you can provide anything that you want. However, you cannot use t as an input. Say, for example, this second function will not compile. This is because t is considered a covariant type. In the converse, you can have a parameter that is only to be used as an input and never as an output. These are called contravariant types, and we usually mark them using the in modifier. If we were to switch out our out with in, then our second function now compiles, but our first function does not. These types of declarations that are done in the definition of the class that accepts a generic is what we call declaration site variance. However, you could set this type of variance inside your usage. This attempt is called use site variance. Let's head back to our animal class. Within here, let's define two methods. One that acts as a covariant and another one that acts as a contravariant. We have defined two methods, produce and consume. The current parameter type t is invariant within the class definition. We can use site variance to provide different types of variance when using this specific class. To do this, we can have another function. Let us call it breed. The function accepts animal A, which has specified that the string can only be output. What we see from here is that the code will compile when we have a.produce. The produce method outputs t. This can work. But in our line 7, the a.consume and then providing in the input cannot compile. Classes and interfaces aren't the only declarations that can have type parameters. Functions can as well. Type parameters are placed before the name of the function. Let us have an example of a generic function. We have a function known as display. This display function takes in a parameter that is an object of the same type. And then we're simply printing out that item. In order to use this, it's the same as how we used our class parameters. So we can have the name of the function followed by the type inside the angle brackets and then provide any necessary parameters. Similar to class generics, the type can be inferred and you can omit the angle brackets with the time. That would still execute. A set of all possible types that can be substituted for a specific type parameter can be restricted by what we call generic constraints. The most common type of constraints in generics is what we call the upper bound. By default, all generics have an upper bound of a nullable any type. This means if you have a generic, for instance with this display, we ideally can use any single thing that we want. We could simply indicate display. Now that would work. We could have display unit. That would also work. Ideally, it can be any single thing that we want. However, sometimes you need to set out some limitations for what your generic can be used for. Let us look at an example as to how we can provide an upper bound. Let us have an interface that defines a mammal object. This interface contains only two functions, gestation and lifespan. We can now set our specific generic to only accept types that are of the mammal hierarchy. So any subtype of mammal is acceptable into the generic. To do so, inside your generic definition in the angle brackets, provide a full colon and then specify the specific type. With this in place, you'll be required to only input items that are of the subtype of mammal. Let's look at an example. If we now display now, this does not compile because it is not of the subtype mammal. If I opted to use the nullable portion, then that would compile. However, if I put any other value like 10, that doesn't compile because it is not a subtype of the mammal type. Let us then create a subtype of mammal. We have an object known as human, which inherits the mammal type, overrides the functions that it's set to override, and then you can simply provide your object in there. In the event that your type parameter needs more than one upper bound, you need to add a separate where clause. The where clause is usually provided after the function definition but before the method body. Similar case to classes. It happens after the class definition but before the function body. Let us create another interface. This interface contains the backbone property. If we wanted our generic to contain both mammal and vertebrate, then I'll need to change the signature of the specific generic definition. Let us see how to do this. Start by removing the upper bound within the type. Before your function body, use the where clause, provide t and the bound that you want it to conform with. Next, you can provide the other type that you want it to conform with. Now we have t is also a vertebrate. You will notice that our human object now does not compile with the display function. But for us to change this, we need to make sure that human satisfies both mammal and vertebrate. In order to do this, we simply want to add another implementation into our object. Now, with both of this implemented, then our code can now compile. The type safety checks that Kotlin performs for generic declaration are usually done at compile time. During runtime, the instances of generic types usually do not hold any information about their actual type argument. This specific information related to the type is said to be erased. Hence, the terminology type erasure. Due to type erasure, there is no general way to check whether an instance of a generic type was created with a certain type argument at runtime. Since that cannot be checked, the compiler will prohibit using any is checks for generic types. But you can check an instance against what we call a star projected type. Let us look back at our animal class. We also have these two classes that we've defined, fish and amphibian. Let us try creating two animals, one of type fish and one of type amphibian. Due to type erasure, we cannot check whether a toad was called with the amphibian type. If we attempted to check whether a generic type is whatever was instantiated with a specific object, we usually get a compilation error. And this is because the type is said to have been erased. Such a confirmation would not work. However, we can use the star projection in order to circumnavigate this. What we can do is we can simply check whether it is an animal as opposed to be an animal of a certain type. And in order to generally do the check, we replace the amphibian type in the angle brackets with a star. Such a check is now possible. Reflection is a set of language and library features that allows you to introspect the structure of your program at runtime. Functions and properties are usually first-class citizens in Kotlin. The ability to introspect them, doing things like learning its name or the type of a property, is usually very essential at times when using a functional or a reactive style of programming. Reflection is readily available within the JVM. However, Kotlin JS Target provides very limited support. In this specific episode, we'll simply speak of reflection with reference to Kotlin that compiles on the JVM platform. The Kotlin compiler distribution usually includes a component required for providing reflection, and it is usually provided as a separate artifact. This is usually done separately in order to reduce the size of the runtime library for applications that would generally not need to use reflection features. To use reflection in a Gradle project, you simply need to add the Kotlin reflect property. You simply need to add the Kotlin reflect artifact in your dependency section and sync your build. One of the most basic reflection features that we use is getting the runtime reference for a Kotlin class. To obtain a reference to a statically known Kotlin class, you can simply use the class literal syntax. We have a simple class known as apples. To get the reference to this class, we will need to just use the class literal syntax. This would provide you with a value of the type K class. With the JVM, the Kotlin class reference is not the same as the Java class reference. In order for you to obtain a Java class reference, you can use the .java property on your K class instance. Let's try and print this out and see what we get. They both have the same type of definition, but one is the Java reference, the other one is the Kotlin reference. References to functions, properties, and constructors can also be called or used as instances of different function types. Let us look at how we can do some function reference. Let us get a list of student scores, in this case 10, 33, 20, 44, 11, and 13. Assuming I want to get a list of all the students that have achieved the pass grade, we can simply use the filter function. This is how you would approach it. Within this case, we can simply indicate we want numbers that are greater than or equal to 20. Store this in a variable known as pass. Just print out the people who passed. As you can see, only 3 people, one with 33, another one with 20, another one with 44. This syntax can be simplified in a different approach. We can have our function defined as follows. You can now pass this function as a reference to the parameter of the filter function. Call it ref passed to just know that we have used the referenced function, scores.filter. Within your filter function, you can provide the parameter, which is your function known as pass score. And with that, if we replace passed with ref passed and print it out, it will have the exact same output, 33, 20, and 44. We can also pass reference to overloaded functions. The compiler will infer the correct type of function that will be needed. So the return type is the same, but the input type is different. We can still use the pass score function to do the same exact functionality. As you can see, even the IDE itself highlights the function that has been called and the one that has not. Though they are the same function name, it's been overloaded with a different signature. And therefore, when calling the filter function, the referenced function will only be the correct signature one. And if you rerun this, it will still remain the same exact 33, 20, 44. You can provide context to which referenced function that you want by putting it inside a variable with that explicit definition. Let us see how this can be done. Assuming you have an added function, takes in a lambda that contains a boolean as a parameter and gives back a boolean as the value, and this entire function returns back a string, then we can define which referenced value we want. So either the pass score with an integer or the pass score with a boolean. One way for us to do this is by just providing the reference to the correct pass score. So we could indicate reference, and this correct reference has that specific type, boolean that returns boolean. Then we can provide the specific reference using our two full colons and provide the pass score. You'll now notice this other pass score now turns green because the IDE can infer that this value that we are calling correct reference, which has a function that intakes a boolean and returns a boolean, and it has been referenced to pass score without providing any parameters. Functions aren't the only things that can be referenced. Properties can also be referenced within classes. Let's have an example of two properties. With these two properties, height and age, we can get references to those specific properties. Now, a reference to a property gives you a Kotlin property type object. Let us look at how this works. Whatever we've printed out contains the identifier, which is val, the name of the property, which is height, and then the type is defined as a Kotlin float. In order for us to get the value of a referenced property, we usually use the get method. This will give us the value within that property. We'll rerun. And now you can see the value is actually 200.5. We can also get the name of that property that we have referenced. To do that, we use the name property within that property reference. And you can see the name of the property is height. We can actually even change the value of that specific property as long as we have the correct reference. To do this, we usually use the set method. For us to implement this, the set method is only available for mutable properties. Therefore, let's change our age to something mutable. Then we can get our age reference. And after that, we can set something for the age reference. So maybe initially the age was 90. Let's now put it at 17. You can print out the value, and the value is 17. Accessing a property that is a member of a class, we usually qualify it with the name of that class. Let us add a property known as radius within this apples class. Have it to the default of 3.0. So we can get this property known as radius using reference. We can have class ref just to represent the property in the class to be referenced, and we can have apples and then provide the radius property. So we can reference that property through the name of the class. On the JVM platform, the standard library contains some extensions for reflection classes that provide a mapping to and from Java reflection objects. This could be something like a method in Java. Let us try and get our Java getter. So to do this, we'll reference the property, and then you just call the property known as Java getter. So if we print that out, rerun this, and you can see the Java getter is public final double apples. Constructors can also be referenced just like methods and properties. You can use them in whichever place that the program expects a function type object, and it takes in the same parameters as the constructor. Consider the following. Let's have a function. If you have a constructor that has the same exact signature as our parameter, we can use it as a reference. We can simply pass a reference to that specific class name as a reference to the constructor in the following way. So we can reference the name of the class if the constructor in that class matches the signature of the parameter set. You can refer to an instance method of a particular object. This can be done as follows. Consider our function here known as ABC inside XYZ, and we probably want to use a reference to ABC. We can use a reference from an instance of XYZ. Have another function. Assuming we want to use this instance function, and the instance function contains a parameter that will be a function that returns a string, and we do have that provided within our method inside XYZ known as ABC. We could pass a reference to that by referring to the instance method itself. Provide our instance. So I'll have XYZ that way, XYZ, say maybe false. Then you could call instance, and within instance you need to provide a reference. So you can do it that way. So you can reference from the instance method. With that, we have come to the end of the penultimate episode in our YouTube series. Our last episode will drop next week, and we'll be speaking about delegation in Kotlin. I hope you've enjoyed this one. Please remember, leave a like, comment, and subscribe. See you in the next one.